Welcome to the deep dive. Today, let's forget just correlation for a moment. We're really going deep into some foundational ideas about a much harder question. How do we actually know if one thing causes another?
It's such a critical question, isn't it? For, well, almost every field. Did a policy actually work? Did this medicine cause the improvement? It's tough because, you can't just rewind the clock in the real world.
Exactly. You can't see the alternate reality. And to help us navigate this, we're looking at excerpts from really a landmark book, Causal Inference for Statistics, Social, and Biomedical Sciences by Imbens and Rubin.
Yeah, these guys are basically architects of modern causal thinking. Their work gives us a structured way to approach this whole problem.
So our mission today is to kind of unpack their main framework, this potential outcomes idea, and see how it helps us design studies, analyze data, and make, more credible causal claims.
It can get a bit technical, sure, but the core concepts are super insightful.
Definitely. We'll guide you through the key ideas and maybe some surprising details. So first things first, what does cause even mean in this setup?
Right. So fundamentally, causality here is tied to an action, manipulation, an intervention, something applied to a unit. That could be a person, a company, a classroom, anything.
Like, did taking this specific aspirin make my headache go away? I'm the unit, taking the aspirin is the action.
Precisely. And the key insight, really the starting point for everything, is that for a causal statement to even make sense, that unit, you, in this case, could have experienced something different at the exact same time.
Okay, so I took the aspirin, but I could have not taken it.
No,
Or taken, say, a sugar pill.
Exactly. The alternative possibility has to exist, conceptually at least. And this leads straight to the idea of potential outcomes.
Potential outcomes.
Yeah. For you, with that headache, there were two potential futures right at that moment. The outcome, if you took the aspirin, maybe the headache disappears. And the outcome, if you didn't take the aspirin, maybe it sticks around.
So before I actually pop the pill, both possibilities exist in theory. I can imagine either one.
Yes, you can conceive of them. They're a priori observable, as they say. But, and this is the crucial bit after you act, a posteriori, you only get to see one of those outcomes.
Right. I took the aspirin, headache gone, but I'll never truly know what would have happened right then if I hadn't.
You can't split yourself in two and live both realities. And this, the book terms the fundamental problem of causal inference.
The fundamental problem, because you can only ever observe one potential outcome for any single unit at a given point in time.
Spot on. You can't know, for instance, what job someone would have gotten without a college degree once they've already finished it. That counterfactual outcome is missing.
It seems simple when you put it like that, but it really underpins everything. It means the actual causal effect for one individual comparing their two potential outcomes is inherently unobservable just from their data.
Exactly. Which immediately tells you why we need more than one unit.
Okay, yeah, that makes sense. If we can't nail it down for one person, we need groups of people, right, to estimate effects on average.
Precisely. We move from the impossible individual effect to estimating average effects.
Huh.
But to do that legitimately, to compare a treated group and a control group, we need another really important assumption.
Which is?
It's called the stable unit treatment value assumption, or SUTVA for short.
SUTVA, okay.
It sounds technical, but the idea is pretty straightforward. It's got two parts. First, no interference. My potential outcomes shouldn't depend on whether you got the treatment or not.
Okay, so what happens to me only depends on my treatment, not someone else's in the study. Makes sense for aspirin, maybe less so for, like, a vaccine.
Exactly. That's a key limitation to keep in mind. The second part is about the treatment itself. There's only one version of each treatment level. The aspirin you took is the same kind as the one I might take. No hidden variations.
Right, not like one therapy group getting way more intense sessions than another group also called therapy.
Precisely. Yeah. And the book is very clear. SUTVA is an assumption. You assume it based on your knowledge of the context. You can't just prove it from the data you collect.
But it's necessary.
Well, the argument is that drawing causal inferences without some kind of assumption like SUTVA is basically impossible. So you have to be explicit about it. If SUTVA is violated, like with that vaccine example, or different treatment versions, you need more advanced methods.
Okay, so we have units, potential outcomes, the fundamental problem, and SUTVA keeping things stable. What's the next big piece?
The next crucial element is the assignment mechanism. How do units actually end up getting one treatment versus another? This is central to everything that follows. It really dictates what kind of analysis you can do and what assumptions are needed.
Ah, so this is where the difference between, say, a clean clinical trial and just looking at survey data comes in.
Exactly. Let's start with the cleanest case.
Yeah.
Completely randomized experiment.
The gold standard, right?
Generally, yes. Because here, the researcher has total control over who gets what, and it's purely based on chance. Like flipping a coin for each participant.
And the real power there is that if you have enough people, the groups you create, treated, and control should look really similar on average, right? Not just on things you measure, but on everything.
That's the beauty of it. Randomization ensures that, in expectation over many potential experiments, all those pre-treatment characteristics, the covariates, whether you measure them or not, are balanced between the groups. It breaks the link between potential outcomes and treatment assignment.
Which makes estimating the effect much more straightforward. The book mentions a few ways to analyze these experiments, starting with Fisher's approach.
Right. Fisher focused on a very specific question.
Hmm?
Testing the sharp null hypothesis.
Yeah.
That's the hypothesis, that the treatment had absolutely zero effect for every single unit in the study.
Zero effect for everyone. That
Right.
seems sharp.
It is. If that null hypothesis is true, then each person's outcome was fixed before the coin flip. Their observed outcome would have been the same whether they got treatment or control.
So how does Fisher test that?
He calculates the probability of observing the results you got, or something more extreme like the difference in average outcomes, just by chance, under all the possible ways the random assignment could have turned out, assuming that sharp null is true. It gives you a key value.
Okay, so it's a test against the idea that the treatment did literally nothing for anyone. What about Neyman's approach?
Neyman was more interested in estimating average treatment effects. What was the effect on average for the people in this specific study? The finite sample effect? Or maybe for some larger population they represent, a superpopulation effect?
So not zero for everyone, but what's the average difference?
Exactly. And the great thing about randomization is that the simple difference in M means the average outcome in the treatment group minus the average outcome in the control group is an unbiased estimator for that average treatment effect in the sample.
Simple difference works. But the book mentions you can still use covariates, pre-treatment variables, in the analysis here. If randomization already balanced things, why bother?
That's a great question. You're not adding covariates to fix bias randomization took care of that, on average. You add them to increase precision.
Ah, to get a tighter estimate.
Right. If you control for things that explain some of the variation in the outcome, like baseline health in a medical trial, you can reduce the noise and get a more precise estimate of the treatment effect, smaller standard errors.
Which naturally leads to using regression methods.
Yes. You can run a regression of the outcome on a treatment indicator, often including those covariates. The coefficient on the treatment indicator gives you an estimate of the average effect, adjusted for the covariates to boost precision.
And they also mention model-based or Bayesian methods.
This involves explicitly modeling the potential outcomes, often as functions of covariates. You use the observed data to learn about the model parameters and, essentially, impute the missing potential outcomes. Randomization helps here too, making the results less sensitive to getting the model exactly right compared to observational data.
Okay, so complete randomization is the baseline. But there are variations, like stratified or randomized experiments. What's the idea there?
You first divide your units into subgroups, or strata, based on important characteristics, maybe things you think strongly predict the outcome. Then you randomize treatment within each of those strata.
Like in that big Project Star study on class size they randomized within schools, right?
Exactly. Stratifying ensures balance on those key variables you chose, which can really increase the precision of your overall estimate, especially if those strata are strongly related to the outcomes. But your analysis then needs to account for that stratification.
Makes sense. And what about pairwise randomized experiments?
That's a special case, often used when you can form very similar pairs of units, maybe based on pretest scores or other characteristics. For each pair, you randomly assign one unit to treatment and the other to control.
Like the Youngstown TV workshop example they mention.
Right. The standard way to analyze that is just to calculate the difference in outcome within each pair and then average those differences across all the pairs. Again, covariates can sometimes improve precision even further.
All right, so that covers scenarios where the researcher controls the assignment, ideally randomly, but often that's not the world we live in. What about observational studies?
Ah, yes, the Wild West, in some ways. Here, the researcher doesn't control who gets the treatment. People choose things, doctors decide things, policies apply to some places and not others. Assignment isn't random.
And the immediate massive problem is that the groups getting different treatments are likely different from the get-go, right?
Yeah. Absolutely. That's the core challenge. Confounding. The people who chose the treatment might be different, maybe healthier, maybe more motivated, maybe richer than those who didn't, in ways that also affect the outcome you care about.
So you see a difference in outcomes, but you can't tell if it's the treatment or those pre-existing differences.
Exactly. So to even attempt to make causal claims from observational data, you need a really critical assumption. It's often bundled under the idea of a regular assignment mechanism, but the key part is unconfoundedness.
Unconfoundedness, that sounds important. What does it mean practically?
Informally, it means that you've measured enough pre-treatment variables, covariates, such that within any group of units that had the exact same values on all those measured covariates, the actual treatment they received is essentially random with respect to their potential outcomes.
Okay, hold on. So if I have two people who look identical on everything I measured before the treatment age, income, past health, whatever unconfoundedness assumes that whichever one got treated and which one didn't was basically like a coin flip, given they looked the same on my measurements.
That's the essence of it. Conditional on the observed covariates, treatment assignment is independent of the potential outcomes. It's like saying assignment was randomized within these covariate-defined cells.
But wow, that feels like a huge leap of faith, and the book hammers this home. It's not testable from the data itself.
Absolutely crucial point. It's untestable because you never see both potential outcomes for anyone. You can check if your covariates are balanced after adjustment, but you can't directly check if the potential outcomes were independent of treatment, conditional on those covariates. You have to argue, based on subject matter expertise, that you've measured all the important common causes of treatment and outcome.
The Lalonde job training data example they use really drives this home, right? The raw comparison looks terrible.
It's a classic. The people who enrolled in the training program were vastly different from the comparison group drawn from a general population survey on things like prior earnings, earned 75 in their data. And since prior earnings are a huge predictor of future earnings, the outcome, ignoring those differences leads to massively biased estimates.
So in observational studies, the name of the game becomes trying to adjust for or control for these pre-existing differences in covariates.
Exactly. And the book details several strategies for doing this. A really central tool is the propensity score.
Right, the probability of receiving the treatment given your observed covariates.
Yes. And it has this remarkable property. If the unconfoundedness assumption holds given your set of covariates, then conditioning on the propensity score alone is enough to remove bias due to all those observed covariates.
Whoa, so instead of trying to match or adjust on potentially dozens of variables, you can just adjust on this one single score.
In theory, yes. It acts as a balancing score. If you compare treated and control units that have the same propensity score, their distributions on all the original covariates should be balanced on average. It's a powerful dimensionality reduction technique. The book even mentions that sometimes working with the log odds of the score, the linearized propensity score, can work better for achieving balance.
Okay, so how do we use this propensity score or the covariates directly? What are the main methods?
One common approach is subclassification, sometimes called blocking.
Grouping people based on their score.
Right. You estimate the propensity score for everyone, then maybe divide the range of scores into, say, 5 bins or strata. Within each bin, the treated and control units have roughly similar propensity scores, and thus should be more balanced on the original covariates.
Like they showed with the Lalonde data, analyzing within those propensity score blocks.
Exactly. Though balance might not be perfect within the blocks, so the book often recommends combining subclassification with regression adjustment inside each block to further reduce bias and improve precision.
Makes sense. What about matching?
The idea here is intuitive. For each treated unit, find one or more control units that look very similar in terms of their covariates, or maybe their propensity score.
Create a pseudo-control group that looks like the treated group.
Precisely. You build a new, smaller data set of matched units where the covariate distributions are much closer.
They talk about different ways to measure similarity, right? Like Mahalanobis distance versus just using the propensity score. And different algorithms.
Yes, there are choices to make about the distance metric and the matching algorithm, like greedy versus optimal. But the absolutely critical step, emphasized strongly, is to check covariate balance after matching. Don't just assume it worked.
How do you check?
Using things like standardized differences in means for each covariate, comparing distributions with QQ plots or histograms, especially looking at the balance of the propensity score itself in the matched sample. The Rhenish barbiturate data example compares Mahalanobis and propensity score matching on how well they balance lots of covariates.
Okay, matching makes sense. Then there's trimming. What's that about?
Trimming involves removing units both treated and control whose propensity scores fall outside the region where the scores for the two groups overlap.
So if you have treated folks with super high propensity scores, but basically no control folks with scores that high, you just drop those treated folks from the analysis and vice versa at the low end.
Exactly.
Mm-hmm.
Because it's really hard, maybe impossible, to find good comparisons for those units. Think about the Connors study on right heart catheterization they mentioned.
What's the trade-off?
You improve internal validity. The estimate you get for the remaining overlapping sample is likely less biased because the comparison is more credible. But you sacrifice external validity. Your findings might not generalize back to the full population you started with, only to the subset with overlapping propensity scores.
Got it. Improve compare-link quality by potentially changing who you're talking about. And the last main strategy, weighting.
Right, methods like inverse probability of treatment weighting, IPTW, often using the Horvitz-Thompson estimator framework. Here, you weight each unit by the inverse of their estimated propensity score, or 1 minus the score for controls.
What does the weighting do?
It essentially creates a pseudo-population where the covariate distributions are balanced between the weighted treated and control groups, mimicking what you'd get in a randomized trial. It's another way to adjust for confounding based on the propensity score.
Okay, so lots of tools, subclassification, matching, trimming, weighting, all aimed at trying to recreate the balance that randomization gives you automatically.
That's the core idea. And it's worth remembering, as the book points out, that we might be interested in different causal questions, different estimates.
Right, not always just the average treatment effect.
Yeah, maybe you care about the effect on the median outcome, or on some measure of inequality like the Gini coefficient. The book notes that policy often focuses on these simpler marginal estimates, like average or quantile effects, because estimating effects that depend on the joint distribution of both potential outcomes for the same person is much harder and requires even stronger assumptions.
Given that observational studies rely so heavily on that unconfoundedness assumption, and we know it's untestable, how can we ever feel comfortable? How do we check its plausibility?
Great question. You can't prove it, but you can do things to gain or lose confidence. The book suggests a couple of clever strategies. One is using pseudo-outcomes.
Pseudo-outcomes. Fake outcomes again.
Kind of. You choose a variable measured before the treatment happened, one that the treatment definitely couldn't have affected. Often this is a lagged version of the actual outcome variable.
Ah, okay. So if I'm studying a training program's effect on earnings in 2024, I could use earnings in 2022 as a pseudo-outcome.
Exactly. Then you run your whole causal inference analysis, propensity score matching, regression adjustment, whatever, pretending that this pre-treatment variable is your outcome. You try to estimate the causal effect of the treatment on it.
Again, if you find an effect.
If you find a statistically significant effect of the treatment on a variable that you know it couldn't have influenced, that's a big red flag. It suggests your adjustments didn't fully account for the pre-existing differences between the groups, casting doubt on the unconfoundedness assumption for your real outcome, too.
That's smart. A built-in reality check.
Yeah, it's really useful. Another approach is using pseudo-treatments.
Okay, what's that?
Here, you compare outcomes between different groups that, according to your theory and covariates, shouldn't have systematic causal differences relative to each other. If, after adjusting for covariates, you still find big differences between these pseudo-treatment groups, it again makes you worry that your covariates aren't capturing all the relevant confounding.
Can you give an example?
Maybe comparing different types of controls in the Lalonde data. If your model assumes unconfoundedness holds for program participants versus control group A, given covariates, does it also hold when comparing control group A versus control group B? If not, something's likely wrong with the assumption or the covariates.
So these checks can shake our confidence in unconfoundedness. What if we are worried or just want to be cautious?
The book touches on a couple of paths. One is calculating bounds.
Setting limits on the possible effect.
Sort of. In some simple cases, you can figure out the range of possible values for the true causal effect that are logically consistent with the observed data, without assuming unconfoundedness. The problem is these bounds are often extremely wide, maybe from -50% to +50%, and include 0, meaning they don't tell you much unless you have very strong prior information.
Yeah, not super practical if they're that wide. What else?
A more common approach is sensitivity analysis. Rosenbaum pioneered a lot of this.
How does that work?
It doesn't tell you if unconfoundedness holds, but it quantifies how much hidden bias, how much unmeasured confounding would be needed to change your conclusion. You ask, how strong would an unobserved confounder have to be related to both treatment and outcome to make my statistically significant effect disappear or appear if you found none?
So it tells you how robust your finding is to potential hidden confounders.
Exactly. It gives you a measure of how sensitive your result is to violations of that key unconfoundedness assumption. The lottery data example shows how plausible levels of confounding could flip the conclusions.
Okay, this framework covers a lot. We've done pure randomization, observational studies with all their challenges. What about situations kind of in between, where assignment might be random, but people don't necessarily do what they're assigned?
Ah, yes, the issue of noncompliance. This is super common in practice. Think of randomized encouragement designs.
Like randomly encouraging people to get a flu shot.
Right. The encouragement is randomized, but actually getting the shot isn't. Some encouraged people won't get it, some not encouraged people might get it anyway. The assignment is clean, but the treatment received is messy.
So the random assignment acts as a kind of nudge.
Exactly. In this setup, the random assignment becomes an instrumental variable for the treatment actually received.
And using 5E requires its own set of assumptions, right?
Yes, key ones. First, the exclusion restriction. The instrument, the encouragement, can only affect the outcome, like getting the flu, through its effect on the treatment received, getting the shot. It can't have some direct effect on the outcome otherwise.
Okay, the encouragement itself doesn't make you less likely to get the flu. Only getting the shot does.
Right. And second, monotonicity. This basically rules out defiers. It assumes there's no one who would only get the shot if they weren't encouraged and only skip it if they were encouraged. People either comply with the encouragement or always do the same thing regardless.
Assuming those hold, what effect can we actually estimate? We can't estimate the effect for everyone because not everyone's behavior was changed by the encouragement.
Precisely. The group whose behavior is changed by the instrument are called the compliers. These are the people who get the shot if and only if they are encouraged.
They follow the nudge.
Exactly. And the causal effect that standard IV methods identify is the average treatment effect specifically for this group of compliers. It's called the local average treatment effect, LA8, or sometimes the complier average causal effect, CTE.
So it's not the effect for everyone, just for those whose treatment decision was actually influenced by the random assignment.
You're correct. Because they're the only ones for whom the instrument actually switched their treatment status, allowing us to leverage the randomization.
How do you estimate it? The book mentions moment-based methods.
Yeah, often using the ratio of intention to treat, ITP effects. You estimate the effect of the assignment, encouragement, on the outcome, and divide it by the effect of the assignment on actually receiving the treatment, the proportion of compliers.
Okay, effective encouragement on flu, effective encouragement on getting the shot.
Roughly, yes. And there are also model-based approaches, often Bayesian, that model potential outcomes and compliance types, which can be more flexible for incorporating covariates. The flu shot data and the Angrist draft lottery studies are classic examples they discuss in this IV context.
Wow. Okay, we have definitely covered a huge amount of conceptual ground here, tracing the logic from Imbens and Rubin's framework.
It's a really powerful way of thinking. We started with that core idea, potential outcomes, and the fundamental problem that you only see one.
Right. The counterfactual is always missing for an individual, which led us to the power of randomization, where the assignment mechanism does the heavy lifting to create comparable groups.
And then into the challenges of observational studies, the absolute necessity of the unconfoundedness assumption, and all the tools developed, propensity scores, matching, weighting to try and approximate what randomization gives us.
Plus, ways to check if that assumption seems plausible, like pseudo-outcomes, and what to do if we're worried, like sensitivity analysis.
And finally, tackling non-compliance with instrumental variables, realizing we might only be able to estimate effects for specific subgroups like the compliers.
Reading through this, the real value seems to be the clarity it provides. It forces you to be explicit about the causal question you're asking and, crucially, the assumptions you must make to answer it with the data you have.
Absolutely. It moves causal inference away from just running regressions and hoping for the best towards a much more principled approach based on understanding the assignment mechanism and potential outcomes.
It definitely makes you appreciate just how hard causal inference is, especially outside of those ideal randomized settings.
No question about it.
So maybe a final thought for you, our listener, to chew on. We've seen that drawing causal conclusions, especially from observational data, often hinges on assumptions like unconfoundedness that we can't directly test. And even our best methods might only give us answers for specific subgroups, the compliers, or those in the region of overlap. How does really internalizing this framework change the way you look at causal claims you encounter every day? Whether it's in a news report about a study, a policy debate, or even just an advertisement claiming some effect.
Yeah, it's something worth thinking about as you navigate all the causal assertions out there.